Hello, my name is Sam Black, and today I am presenting multiview classification using hybrid fusion and mutual distillation, co-authored with Richard Souvenir. Multiview collections can be divided into two types, cross-view and unstructured. In the cross-view setting, each collection is comprised of a structured set of typically two views of the same object, with each view highlighting a specific feature. Cross-view collections are prevalent in the medical image analysis domain. In this example, each collection consists of both a frontal and a lateral chest X-ray, highlighting two different perspectives. In contrast, the views in an unstructured collection do not have any rigidly prescribed order, and the perspective or pose of each individual view can vary greatly. The number of images can also vary from collection to collection. Unstructured collections are common in many scene recognition tasks, such as these examples from the task of fine-grained hotel identification. Modern methods for classifying collections, whether cross-view or unstructured, all typically function in the same general manner. First, initial features are extracted from each individual view, then these features are fused together to be further processed and ultimately classified. Methods can be broadly characterized as either early fusion, late fusion, or score fusion, which is determined by where in the processing pipeline that the extracted features are fused together. Early fusion strategies will extract low-level features from each image in the collection before aggregating these features together to be further processed through a deeper network. Early fusion strategies are more common for collections where there is a spatial alignment between the views, which is typical in many multimodal prediction tasks, such as, for example, action recognition using a collection consisting of an RGB image and an optical flow map. Late fusion is the most popular fusion strategy where a wide variety of methods have been proposed. In late fusion, deeper features are independently extracted from each view and then combined. Methods for combining these features range in complexity and can be as simple as an average pooling of all the view features together into a global collection representation, which was proposed in multiview CNNs. But examples of more complex methods utilize hierarchical pooling strategies, such as the one proposed in group view CNNs, graph convolutions, such as in hypergraph neural networks, or attention modules, such as in the view-n-gram network. Lastly, we have score fusion methods, which can be considered as an extreme version of late fusion. Here, class-level predictions of each view are generated individually, which are then combined to produce a global collection prediction. Like other fusion strategies, these score fusion methods can also range in complexity. Some do simple element-wise pooling of the individual class distributions. Others are more sophisticated, such as trusted multi-view classification, which outputs the view predictions as parameters of Dirichlet distributions, which are then fused together. That brings us to our method for classifying collections, which uses what we call hybrid fusion, which combines late fusion with score fusion during training. For our method, which we call multiview hybrid, we repurpose an off-the-shelf hybrid CNN image transformer architecture for classifying multiview collections. This is a network that is typically designed for processing single images where the CNN takes in the image and produces a spatial feature map that is then projected into a sequence of tokens. These tokens are then further refined in the transformer where information between the tokens is shared through a series of global self-attention layers. The transformer then ultimately outputs the pre-softmax logit Z, which is then softmaxed to arrive at the predicted class categorical distribution for the input image. To repurpose the CNN image transformer architecture for the multiview setting, we pass in each collection image individually through the CNN first. Then, the tokens from each view are concatenated together into a single sequence and are then further refined in the transformer, with the global self-attention layers processing the features of each view together. This provides each token with collection-wide context. Finally, the pre-softmax logit Z prime is outputted, which represents the collection prediction. This vector is then softmaxed to produce the class categorical distribution. This figure provides an overview in the case when there are only two images in the collection, but our method can accommodate collections with any number of views. In order to train our method, we introduce a novel mutual distillation loss function which involves using the predictions of the individual views to generate a distillation term. These individual predictions are generated by processing each view's tokens by themselves through the same transformer with the same weights. This generates a pre-softmax logit vector for each view in the collection, which in this figure are denoted as Z1 and Z2. Then, these logits, which we collectively refer to as Z arrow, are fused together using mean pooling, which is represented by the function f. We take the softmax of the fuse distribution and, for our mutual distillation term, compute the KL divergence between it and the overall collection prediction. This distillation loss is tailored to the multiview setting by penalizing misalignment of the score fuse logits and the multiview prediction, which greatly improves generalization capability. Moreover, we compute this KL divergence term bidirectionally as it helps with convergence. That brings us to our overall objective function, which is broken down into three parts. First is the cross-entropy loss between the collection prediction and the one-hot class label, which we call LM. Second, we take an average of the cross-entropy loss terms computed between each individual prediction and the class label, which we call LS. And then finally, we have our mutual distillation term, LMD, that is weighted according to a hyperparameter lambda. We first evaluate our method on a cross-view chest X-ray classification task. We use a subset of the Chexpert dataset, where each collection consists of a frontal and lateral chest X-ray of a given patient. Methods are trained and evaluated on 13 binary detection tasks, with example tasks including fracture detection and pneumonia detection. We compare our multi-view hybrid model against a variety of previous approaches that incorporate different fusion strategies using convolutional or transformer-based architectures. We surpass each in the overall task AUC-ROC score. We also evaluate our method on unstructured collections using the hotel's 8K dataset. Here, the task is to predict the hotel out of thousands of possibilities given a collection of images from the hotel. We evaluate against the same baselines as before. This table shows the results with 2 views per collection, and again our method achieves the best performance by a considerable margin. On this slide, we have some examples of collections from hotels 8K that our method correctly predicts. The green border or red border indicates whether the individual view prediction is right or wrong, respectively. This plot shows results for larger collections, where we train and evaluate our method along with 2 of the baselines on hotels 8K with up to 4 images per collection. Generally, as the number of images increases, the accuracy likewise increases, although the marginal gains diminish as more views are added. This is expected as each additional view is more likely to contribute to redundant information that is already present in another view of the collection. But nonetheless, the marginal gains for our approach are still far greater than that of the baselines, which both degrade at 3 images. We perform an ablation study on the 3 components of the loss function, the single image cross-entropy term LS, the multi-image cross-entropy term LM, and then the mutual distillation term LMD. For each setting, we train the model and evaluate the performance on hotels 8K with 2 images per collection. All 3 components play a role in the overall performance of the model, as all subsets significantly underperform the full loss function. Notably, including the single image loss, LS helps improve accuracy considerably, where we observe a positive contribution by comparing settings 2 and 3 and then settings 4 and 6. Moreover, our novel mutual distillation term, LMD, also contributes substantially to the performance of the model, and this can be observed by comparing settings 3 and 6, where accuracy increases from 0.612 to 0.651. To better understand multi-view classification, we inspect the class activation maps for the same images in the single view regime compared to the multi-view case. This slide shows the activation maps generated for the pair of images with the model trained for single view classification in the middle row and then for multi-view classification in the bottom row. Typically, when there exists overlapping visual information, it is activated for only one of the views in the multi-view case. In the example on the left, suspension cables are highlighted as a prominent feature in the single view setting. However, for the multi-view setting, the region for the cables remains active for the right image, while the left image adds new salient regions around the road. Similarly, we see this in the second example with the steeple, where saliency shifts in the second image to the building facades. So, to conclude, we introduced a generalizable method called multiview hybrid for classifying cross-view and unstructured collections that outperforms existing approaches on tasks using either collection type. Our method is trained using a novel mutual distillation loss that incorporates score fusion of the individual predictions, which greatly boosts the model's overall performance. For future work, we plan on generating a more informative distribution for distillation by fusing the individual view predictions in a manner that considers the total amount of view overlap in the collection. That concludes the presentation. Thank you so much for watching.